Hi everyone, my name is Tudor Cristian Petrescu, and today I will present to you a case study regarding the historical monument Brela Hospital, in short ECH, Pavilion B Section 2, and we're going to talk about the structural analysis and the optimal retrofitting solutions for masonry walls. So we're going to put this a little bit into context. We have a major problem now as humanity, and that's the COVID-19 pandemic, and this has highlighted the lack of emergency hospitals and treatment and care facilities, which of course help in the fight against this disease. And so a lot of countries seek to resolve this problem. There are several solutions which were put forward. One of them is basically to optimize the full capacity use of available spaces in existing hospitals. Hospitals which are not up to standard can also be rehabilitated, and it's also possible to develop new constructions such as so-called mobile hospitals or other sort of temporary facilities that will offer some help. And so in this context, we're going to take a look at the Brela Emergency Hospital. As you can see, is quite a big hospital, but it's a historical building. It's classified as one, as such, and of course it's in need of various sorts of investments and retrofits and upgrades and so on and so forth. So now we're going to take a look at the general layout of the building. As you can see, and it's pretty big and with a rather imposing facade. And then these are the lateral facades. There also exists an inner courtyard and also a backyard. And already you might notice some degradations. There's the plastering is degraded, the windows are of the old type, there's a little bit of water infiltration. This is just at the first look. The building looks like this, actually. So this is sort of a 3D view, but in of course, done in a structural program. And we're specifically going to refer to section number 2, which is in dire need of intervention. This is also called Pavilion B, and this is the one that's been analyzed in this paper. So the thing with it is that, as I told you, it's very old. It's been constructed during the interwar period between 1923 and 1928. It's not a simple structure. It's a rather complicated one. As you could see, besides the rather irregular plan, there are other issues with it. Some stories are just partial. So then we can talk about vertical discontinuity. The masonry type, of course, as it was back those days, it's unreinforced. And the floors are of concrete slabs. Also, the roof is, of course, on a wooden structure, and it's covered with ceramic elements. Moreover, there are other issues, such as the foundation soil, which is sensitive to moisture. And the foundation is also the old type. It is continuous, but it's of course laid on stone or boulders. And if we are going to look a little bit of the assessment of the physical condition, there has been observed the capillary rise of water, the effects of freeze-thaw, and of course mortar degradation. There is also a partial foundation soil collapse in the central area. Due to different heights of stories and different, therefore some difference in structural mass. But there is no degradation regarding the reinforced concrete slabs. And even better, there was no significant seismic damage observed throughout the service life of the building. Now, if we go a little bit into the construction specific details, as I've said before, the masonry walls, together with all the ramifications and intersections, are properly weaved but are not reinforced. The quality of masonry seems to have been proper, and there are also reinforced concrete belts which are good for the transfer of mass and inertial forces. And there also exist lintels. Unfortunately, there is no data available regarding the previous interventions that have been made on the construction, and there is also no data regarding the door and window openings which might have been created during the lifetime of the structure. Unfortunately, coming back to the structural elements, there is a high vulnerability regarding the masonry work and the long rows of expelled mortar. Also, the fact that there is no waterproofing doesn't help the entire situation. Other than that, the other aspects are rather standard. The foundation seems to be to a reasonable depth or height, which is 4 meters. And the site on which the hospital has been built is flat. And so I'm going to show you a little bit what has been observed during the structural analysis, and then we're going to talk further in detail. So, of course, there was a model analysis done, and we can see a little bit of lateral displacements in the eigenmodes of the vibration of the structure. So that's for the first eigenmode. You can see that the lateral big facade, for example, it shows signs of displacement. Is the same in the top view, so we can see that basically the entire facade has a tendency to run away from the structure, so to speak. That's the same for the second eigenmode. It doesn't really look better. There's a pronounced tendency of collapse with outer expelling of the brick and mortar. And again, this is confirmed by the third mode of the structure. So things so far are not looking very good regarding the computer simulations, the results there. Of course, it is possible to check the model period, frequency, the participation ratios, and the drift and the average drift, but you can find all these details and other technical data in the full article. So then, as I said, a global analysis was performed for section number 2. If you are going to ask why it hasn't been done for the entire hospital, this is because the seismic verification is quite complex and the amount of data to be processed is rather big. So for the purpose of this paper, we will only refer to the section number 2 of the hospital. What happened was that the entire section was taken, it was analyzed, and then for easier subsequent calculations, it was partitioned into 5 modules. And then a seismic analysis was made. And so, as I've shown you before, the local translation effect was observed. And conversely, so on the rather good side, the model road participation ratio is consistent on the global y direction. And of course, then the drift and the average drift resulted, which are useful for the design spectrum method of the seismic loading. Furthermore, what can be observed in the dynamical analysis is the so-called lateral drift with large lateral rigidity. And furthermore, I will show you the virtual work volume, which will illustrate basically which sections become active when the structure starts to dissipate the seismic energy induced by the earthquake. So here you have a graphical representation complete with a colored scale for the x and y directions, respectively, of the structure. So we can see there is a little bit of lateral displacement, and the relative work and volume for the structural memory system. And so we can look on even more graphs. So these are the maximum story displacements, and we can see just like it was in the first pictures that I've showed you with the eigenmodes, around story 2, more or less, is where let's say a first collapse or failure would be expected of the masonry. The story shears are also rather evident. The two different colors are from the two different directions. There is also overturning moment, and also their maximums, which will show around story 1. And then, of course, the analysis goes into the calculation regarding the strength capacity determination. So basically, how much strength is there left in the building? And for this purpose, according to the P100-3 standard, the 3 possible failure mechanisms were considered: the eccentric compression failure, the horizontal sliding failure, and diagonal cracking mechanism. And so the minimum value of the shear force, of course, associated with these 3 different masonry mechanisms, represents the capable strength value of this effort. Of course, you can find, again, the technical data and the relevant equations that were used and the results obtained in the full paper text. And, of course, what happens is that all the masonry piers are numbered, and then they are analyzed. You'll find, again, in the paper, a huge table which summarizes the obtained results and shows exactly which piers are vulnerable and which are less. So to verify the lateral strength capacity, the level 2 methodology was used. And what happens, the value is that the values of the sectional design effort were compared with the ultimate limit state, and the value of the R indicator, which basically confirms the seismic risk of the structure, will appear. This is something that happens in any technical expertise. The R3 indicator was established. The R1 and R2 weren't, because this is just a presentation of how the analysis and further intervention suggestions were made and were carried out. This is not a technical expertise. And so we can see that the seismic response of the structure is, however, favorable, and the lateral structure doesn't present deficiencies, but nevertheless there is a need for intervention. And furthermore, there was made a different risk class for X direction and for Y direction. So for the X direction is 4, and for the Y direction is 3. And so a representation was made regarding the masonry walls that need intervention. These are the walls on which some interventions should be carried out. Finally, because the intervention is rather complex, and the classical intervention would require the personnel to be evacuated and the hospital to be inactive for a few months, probably the most useful intervention that can be made would be with composite materials. And you have here several representations of them. It's a quick and easy method to rehabilitate, and it would restore the bearing capacity of the structure. Thank you for your attention.